In the previous video, we have seen the relationship between direct lattice and reciprocal lattice through a Fourier transform. If we take the Fourier transform of a direct lattice, we obtain a reciprocal lattice, and if we take a Fourier transform of a reciprocal lattice, we obtain direct lattice. And we have discussed what Bragg's law is and its diffraction conditions, and we were able to see that obtaining a diffraction pattern means taking a Fourier transform. Obtaining a diffraction pattern means taking a Fourier transform, and that diffraction pattern we have obtained is a representative of the reciprocal lattice of the direct lattice of the crystal that we are studying. Okay. While taking an X-ray diffraction pattern, the image we obtain will be like this. It is a diffraction angle versus intensity plot, but the real diffraction pattern that we observe in the XRD device is different. It's actually here we observe only the intensity versus angle plot, but the real diffraction pattern that we obtain in the XRD device will be like this. Here test crystals real diffraction pattern is analyzed, and as you can see, it almost looks like a reciprocal lattice that we have discussed yesterday. These black dots denote reciprocal lattice points of different planes of a direct lattice crystal. So when you compare with the previous slide, you can see that taking a diffraction pattern is equivalent to taking a Fourier transform, and taking a Fourier transform essentially means taking a direct lattice to its reciprocal lattice. I hope you understand these relations. Now let's try to understand scattered wave amplitude. And scattered wave amplitude means in the diffraction pattern that we have obtained in an XRT, we have intensity versus Bragg's angle plot, and you can see different planes have different intensities, and we have to analyze why different planes have different intensities. So and different intensity and amplitude are related, so here we are trying to understand how the scattered wave amplitude we are trying to analyze the scattered wave amplitude using Fourier analysis, or using the Fourier analysis. Now the scattered wave amplitude depends on the spatial distribution of electrons within each cell. In a lattice, this is lattice, and lattice is an imaginary points, and we have different kinds of atoms or molecules placed in these lattice points that makes it a crystal lattice, and each of these molecules will have electron cloud around them, and this scattered wave amplitude will be dependent on that electron cloud present around each lattice point. Now in a direct lattice like this, a crystal is invariant under translation operation T. Okay, a translation operator means taking it's a vector that takes us from a lattice point like this to another lattice point which have identical environment as of the first lattice point. We are taking T takes us from this lattice point to this lattice point. It takes from 1 to 2, and both this 1 and 2 should have identical environments like charge concentration or electron number density. All these properties must be conserved while taking a translation operator. Okay, and a translation operator can be denoted by U1, A1 plus U2, A2 plus U3, A3, and A1, A2, A3 are the are the crystal axis. A1, A2, A3 are the crystal axis about these three directions, x, y, and z, and u1, u2, u3 are integers. Okay, so translation vector t can be expressed like this. Okay, and as I told you earlier, that local physical properties do not change with a translation operator, like charge concentration and electron number density doesn't change with a translation operator. And as I told you earlier, the scattered wave amplitude depends on the spatial distribution of electron density. So here we are trying to analyze electron number density in the following section to understand the scattered wave amplitude. Okay, here we choose n of r as the electron number density, and it's a periodic property. It will have a periodic property because here we have some electronic density, and in the next lattice point that exists after a small distance a called the lattice constant, we have the next molecule, and it will have a electron density around it. So the lattice, the electron number density n of r is always a periodic property. So with the translation operator t, that property will not change. Now, so using that property, we can write n of r like this: n of r plus t is equal to n of r, because it's a periodic property. So after doing a translation operator t, we will have the same conditions as we had before. Okay, so n of r plus t is equal to n of r. Now we are trying to incorporate the Fourier analysis, or using the Fourier transform technique that we have told in part 1. Okay, the properties of crystals are directly related to the Fourier components of electron density. So if this point have some electron density, I can unpack this electron density, or let it be like this. This is the lattice point, and electron densities are like this. Okay, it have a higher electron density, and this place have a lower electron density, and then we have a higher electron density region, and it continues periodically. Okay, and I am trying to unpack this electron density region, or this electron density in this region, using Fourier analysis. Okay, or I am trying to take a Fourier transform of this electron density. As I told you earlier, that a Fourier transform is unpacking the various components or the various frequencies that are incorporated in a wave. So if you have a wave like this, I am trying to unpack that wave into a very large number of sine waves of different frequencies and amplitudes, and that are summed up to obtain this final resultant wave. So if I have a electron density of a periodic nature, I am trying to unpack this wave or electron density with a periodic nature to a large number of frequencies, component frequencies, and try to analyze it using Fourier transform. Now, initially we consider a one-dimensional lattice arrangement, like this. Okay, and we are trying to analyze the electron density of this one-dimensional lattice arrangement of the crystal with Fourier transform. So as I told you earlier, this electron density can be unpacked into a large number of frequencies or large number of frequency components using Fourier transform. So here we are doing that, expanding n of x, or the electron density, in a Fourier series. N of x equal to n0 plus summation of a large, here we use as a the Fourier components are taken as a mix of sine waves and cosine waves. So we have summation here. So a large number of waves, or sine waves and cosine waves, are taken, and the mix of it gives, and they are mixed together to give this n of x. Means a large number of waves of different frequencies are mixed together to give n of x, the electron density. And or in the other way we can say that n of x, or the electron density, is composed of large number of frequencies using, and we can analyze that frequencies using a Fourier transform. Here Cp and Sp are constants, and cos 2 pi p is an integer, and a is p is an integer, and a is a lattice constant. Is a lattice constant between two adjacent lattice points. Okay. So Cp cos 2 pi px divided by a plus sine Sp sine 2 pi px divided by a. Now we try to understand electron number density at a point n of x plus a. At a point x plus a, electron density at a point x plus a. A is a lattice constant of that lattice. Okay. Now we know the equation n0 plus cos term plus a sine term. So we substitute for 2 pi px by a instead of x by a. We instead of x we put x plus a, and we can split it this into 2, and we get 2 pi px by a plus 2 pi pa by a, and we can cancel these two a's. So n0 plus summation or Cp cos 2 pi px by a plus 2 pi p plus Sp sine 2 pi px by a plus 2 pi p. And we know this is cos theta plus 2 pi p is an integer value, so we don't have to bother about it. Cos theta plus 2 pi, it's cos theta only, and sin theta plus 2 pi is sin theta only. So we can write these two terms as n0 plus summation Cp cos 2 pi px by a plus Sp sine 2 pi px by a equal to, and this is the n of x value that we have seen in the previous slide. So it's equal to n of x. So what we have find is n of x plus a is equal to n of x. So we have proved the periodic nature of the electron number density in that crystal lattice. Now we are going to incorporate the two concepts that we have discussed earlier, the reciprocal lattice and the Fourier transform. And I told you earlier that the Fourier transform is taking Fourier transform means taking from the direct lattice points to it means that taking a direct lattice to reciprocal lattice. So here the 2 pi p by a term, we say the 2 pi p by a is a point in reciprocal lattice. It is a point in reciprocal lattice and over the Fourier space of the crystal. Okay, so why this, the meaning of this word is clear as we have discussed it in the previous slide, in the previous part. Okay, the Fourier taking a direct lattice to Fourier space means taking a direct lattice to reciprocal lattice. Okay, so this reciprocal lattice points are denoted by 2 pi p by a, and we obtain this 2 pi p by a from Fourier expansion. So I hope you can make those connections. Okay. Now the reciprocal lattice points tells us the allowed terms in a Fourier series. So we can make any we know that a Fourier series expansion means a large number of sine and cosine waves are mixed. So which all sine and cosine waves have to be mixed, and what about the amplitude or so 2 pi p by a tells about the phases of that cosine sine waves, sine waves and cosine waves that we use in the Fourier analysis. Now a term is allowed if it is consistent with the periodicity of the crystal. Okay, so a term in the reciprocal lattice can be taken. So a particular value for this can be taken if it is consistent with the periodicity of the crystal. Periodicity is given by A. So other points in the crystal space are not allowed in the Fourier expansion of the periodic function. So we have some functions or some cosine values to we have some sine waves to take and some sine waves to ignore. So if we, the sine waves that we have to take is is given by this 2 pi p by a term, and it is a reciprocal lattice term. So we have this is a electron density versus the lattice one-dimensional lattice X plot. So we can see a periodic periodic nature of this electron number density, high, low, high, low. You can see it. So this electron, this high or low, is related to points in reciprocal lattice. The 2 pi p by x, 2 pi p by a's that we say that they are reciprocal lattice points, and these electron densities have a corresponding reciprocal lattice points, and those this is 2 pi into 1 by a, this is 2 pi into 2 by a, and these this is a reciprocal lattice. Okay, these points in reciprocal lattice shows the corresponding, these points in the reciprocal lattice shows the corresponding electron density maximas, or the maximum electron densities in a direct lattice. The maximum electron densities in a direct lattice can be represented as points in reciprocal lattice, and they are given by 2 pi p by a. P is a integer. Now initially we have expressed electron number density n of x using Fourier analysis as a combination n0 plus summation of a sine function and a cosine function. So we can incorporate, or we can write in a more convenient way using exponential. So so e raised to I theta is equal to cos theta plus I sin theta. So we can write this n of x electron number density term in terms of a exponential term. It becomes n of x equal to summation over p np exponential e raised to I 2 pi px by a. Okay, then this coefficient np, the coefficient, we had a coefficient here sp, and we had a coefficient here cp, and now we have a coefficient np that incorporates these two. Okay, as you can see, the coefficient of np is a complex number. So if we to ensure n of x is a real function, n of x is an electron number density, so it must be a real function. So if we want this np, we have summation over p. P can take both positive and negative integers. So if you want to take if you want to obtain a real electron number density function, we must have the complex conjugate of n of minus p must be equal to n of p to obtain a real function. Okay, n star of minus p is a complex conjugate of n of minus p, and if that is equal to np, then we will obtain a real function. So now we are trying to unpack this positive integer terms and the negative integer terms, and we are rewriting this equation as this. So np cos phi plus I sin phi plus n minus p cos theta minus I sin theta equal to, now we are packing the cos phi terms, clubbing the cos phi terms together, np plus n minus p cos phi plus I np minus n minus p sin phi. Now we already have np plus np and n minus p are same, as complex conjugate is same, and we can rewrite this as, which in turn be equal to the real function. So we obtained n of x as a real function to real np cos phi minus 2 imaginary np sin phi. Now we have done all this analysis in a one-dimensional plane, one-dimensional crystal. Okay. Now we are extending this into 3 dimensions. So to extend it to to make things clear, 2 pi p by a is a reciprocal lattice point in one dimension. Now we have to find 3-dimensional 2 pi p by a, or a 3-dimensional reciprocal lattice point, or a 3-dimensional reciprocal lattice point. So we denote that by G. Okay, extending the Fourier analysis into 3 dimensions, we must find a set of vectors G such that vectors G. This is a reciprocal lattice vector. Okay, reciprocal lattice vector G such that n of r is equal to summation over G and G exponentially e raised to I G dot r. So we have seen this equation before. Ng is equal to np exponentially e raised to I 2 pi p x by a. So here 2 pi p by a denotes the reciprocal lattice point. So instead of 2 pi p by a, we must find a vector G in reciprocal lattice point, or a vector G in reciprocal lattice corresponding to the 3 dimension. Now that G must be invariant under all crystal translation T that have that leave the crystal invariant. It must be so because the periodicity of a direct lattice must be preserved in a reciprocal lattice too. So the invariance of invariance while applying a translation vector T must be satisfied by analyzing it in reciprocal lattice, and in that reciprocal lattice we have G as the reciprocal lattice vector, and that G is, tells us about the electron number density using a large number of frequencies. We have summation here, a large number of frequencies composed in the or analyzed when we do the Fourier transform. And in that Fourier expansion, we saw we have an ng, summation of the ng exponential e raised to I g dot r. Okay, we have an ng, and this ng determines the X-ray scattering amplitude. So we are going to find out the scattering wave amplitude in this derivation. So here we see mg as a scattering wave amplitude. So to find ng, we have n of x equal to this equation. So to find ng, we need to inverse this. We have to take the inversion of this Fourier series. So we have so now we are going back to the one-dimensional case. So we have a one-dimensional equation here, n of x equal to this one. So here np, we have np as the scattering amplitude. So to find np, we have to do the inversion of the Fourier series. Now we are doing the inversion, and we get np is equal to a inverse integral 0 to a. To find np, we move all these to other side, and we obtain np is equal to a inverse integral 0 to a n of x e raised to minus 2I px divided by a dx. Okay, we have obtained this. Now we know what n of x is. Okay, n of x, this is the n of x. So we substitute this equation for n of x, and we know the exponential and all terms are there. Np is there. So in order to demarcate between these two, we use a p dash here in the inverted Fourier series, and now substituting n of x here, we obtain summation over p dash n p dash integral 0 to a exponential e raised to I 2 pi into p dash minus p of x divided by a. So using a, here we have p and here p dash, then clubbing these two, we have e raised to I 2 pi p dash minus p x divided by a. Now we have two conditions. Now are these p dash and p equal or not? So we are trying to analyze the two conditions, and if p dash not is equal to if p dash is not equal to p, the value of the integral, if p dash is not equal to p, when we do the integration, we get, doing this integral we get a by I 2 pi p dash minus p e raised to I 2 pi p dash minus p minus 1. Okay, simple integration. Now if p dash and p are not equal, we know both of these are integer values, and if they are not equal, we will get an integer value here. Okay, so e raised to I 2 pi into an integer. So we have an expansion of the form cos 2 pi plus I sin 2 pi. Okay, this will become 0 and cos 2 pi become 1. So we have here we have instead of this term we will have 1 minus 1, and this will become 0. This will be equal to 0. So that is what we have shown here. If p minus p dash is an integer, e raised to I pi into an integer, and it would be equal to 1, and substituting here we will get 0. And if p is equal to p dash, okay, this is the next condition. If p is equal to p dash, we will obtain e raised to so from here we obtain if p is equal to p dash, we get e raised to 0, and e raised to 0 is 1, and while integrating we have integral 0 to a 1 into dx to integrate after putting p is equal to p dash. Then we get it equal to a. In doing this integration we get a, and substituting here we get substituting back into this equation, we will get a inverse n p dash into a. Okay, that's what we have written here. Np is equal to a inverse np into a equal to, and the inverse a equal to 1. So this np is equal to, we will get np dash is equal to np. So this is an identity, and so the scattering wave amplitude in one dimension, that's np that we have found earlier, this is an identity. Np is equal to a inverse integral 0 to a n of x e raised to minus 2 I pi p x divided by a into dx. This is an identity, and extending this identity into 3 dimensions, we get ng. I told you earlier, in 1 dimension we write it as np, and in 3 dimension it will be ng. It will become ng is equal to inverse of volume into integrating over the cell. Here we integrate over the lattice constant 0 to a, because there was one dimension. Now ng is equal to inverse of volume of the cell into integrating over the cell into n of r into e raised to minus I g dot r into dv, and the diffraction conditions will be discussed in the next part. Thank you.